Welcome back, everyone. Let's continue with one more example of curve sketching or complete curve analysis of a polynomial function. This time we're looking at y equals x plus 1 times 1 minus x power 3 times 2 plus x. Let's begin by finding the domain of the function. Since this is a polynomial function, the domain is a set of all real numbers. Now, next, let's determine the range. For the range, we'll examine the powers of each factor, and we see that we have powers 1, 3, and 1, and that will give us information about the degree of the function, which is 1 plus 3 plus 1, or 5. So this is an odd degree polynomial function, which tells us that the range will be the set of all real numbers as well. Now, let's find the x-intercepts. We do this by setting the function equal to 0, which means that the function will be 0 if either factor equals 0. So we'll have x plus 1 equal to 0 at x equals negative 1, 1 minus x equals 0 at x equals positive 1, and 2 plus x is 0 at x equals negative 2. So there are 3 x-intercepts in this function, and let's record them. I'll start with the lowest. So the furthest to the left, negative 2, 0, and then negative 1, 0, and positive 1, 0. Next, we'll find the y-intercept. For the y-intercept, we set x equal to 0. So for y, y would be equal to 0 plus 1, 1 minus 0 to the power of 3, and then 2 plus 0. So this is basically 1 times 2, or 2. So the y-intercept will be at x equals 0, y equals 2. For intervals of increase and decrease, we'll wait until we have the minimum and the maximum. Remember that this is an odd degree polynomial function, so there won't be any absolute maximum or minimum, so we can complete this spot here on the table, and we'll write in here no absolute max and no absolute min. Now, next we can determine the leading coefficient of this function, and for this we look into the coefficients of x in each factor. Now, coefficients here seem to be 1, so the leading coefficient will be, let me write this down, equals 1, the coefficient of the first, and then we have negative 1 to the power of 3. Be very careful, it's very easy mistake to make. We always focus on the number we see first, but remember this variable term here is listed as last, and negative 1 is the leading coefficient of this factor. And then we have 1 to the power of 1. So if you multiply them all, then you will get negative 1. So with the leading coefficient of negative 1, an odd degree polynomial function will behave like a line with a negative slope, which means that the graph will start in quadrant 2 and end in quadrant 4. Now, since we're at it, we're going to plot the x and the y-intercepts. So we have the x-intercepts at negative 2, negative 1, and positive 1. So negative 2, negative 1, and positive 1, they're packed very tightly here together. We could have set a better scale by making the units in the horizontal axis a little bit bigger, but that's okay, it's totally fine. We'll get a very good view of the graph regardless. Now the y-intercept, we said that is equal to a positive 2, and what we get in this case is the y-intercept right here, positive 2. And we know that the graph of the function will start in this quadrant and in this quadrant, and we are ready to sketch the graph, to draw a very simple sketch of it. Remember that our first x-intercept that we're hitting here is negative 2. This is first order x-intercept. So what that means is that we're going to start in quadrant 2 and hit the x-intercept very simply by crossing the x-axis. The next x-intercept of negative 1, let's take a look. X-intercept of negative 1 is order 1, which means that the graph will make a turn in here and hit negative 1. Now, somehow we'll be able to intersect the y-intercept. We don't know exactly whether we're going to intersect this way or we're going to intersect this way, so whether the maximum, the higher point, will be to the right or to the left, but most likely it seems to be on the left side of it because the next x-intercept is coming very soon. And not only that, but this is going to be a third order x-intercept, which means that the y values will change a little bit faster around here. So we are going to approach x equals 1 by making an S shape at x equals 1. And that is because the graph of this function will have the x-intercept right here in an S shape as the x-intercept is a third order. And this would be approximately the sketch of the graph. Is definitely not the graph of the function that we want to, consider as the most accurate, as the best answer. Now, the reason why is because we still have work to do in finding the minimum and the maximum. So the next thing we want to do is start by determining what the local min and the local max is. Now, the local minimum will be somewhere in between -2 and -1. Now, for this, we're going to start with halfway between -2 and -1. And halfway was going to be x equals -1.5. So we're looking at local minimum first. So we're going to choose as our center value -1.5. And the equation of our function, so let's bring it down here, is y equals x plus 1, 1 minus x power 3, and then 2 plus x, or x plus 2. It's easier that way. So what we have in here at -5, so f at -1.5 would be equal to -1.5 plus 1, 1 minus -1.5 to the power of 3, and then -1.5 plus 2. So let's find out what this value equals. So we have -0.5 here. Now, 1 minus -1.5 is 1 plus 1.5, so that's 2.5 to the power of 3, and this is going to be a 0.5. So let's multiply -0.5 by 2.5 to the power 3, and then by 0.5, and we'll get -3.9. Looks like a pretty reasonable answer to me. So what I'm going to do is I'm going to try to check and see if the minimum is exactly here, or maybe further to the left or further to the right. But it's definitely not at -2. We'll fix that. So I'm going to check -1.6. At -1.6, we'll have -1.6 plus 1, 1 minus -1.6 to the power of 3, and then -1.6 plus 2. Let's find out what we get here. So the first one will be -0.6. Again, 1 plus 1.6, 2.6 power 3, and 0.4. So -0.6 times 2.6 to the power of 3 times 0.4 equals -4.2. As you can see, we're going further down, which means that the minimum should be further to the left of -1.5. So we'll check -1.7. Now, there is very little room in between these two x-intercepts, so I doubt that we will have to dig any deeper in the negatives, but we're going to try to make -0.7 to make sure that we get the most accurate answer. So -1.7, then power 3, and then -1.7 plus 2. So -1.7 plus 1, that's a -0.7, 2.7 power 3, and this one would be a 0.3. Let's see what we get. We have -0.7 times 2.7 power 3 times 0.3, and this time I got -4.1. So which means that as I went further down to the left, the numbers start picking up, and that qualifies this particular point right here, x equals -1.6 and y equals -4.2 as the local max. So we're gonna, as a local min, because we're looking at this point. So we are going to plot this point on the table here, let's record it as a local minimum, which is at negative 1.6, negative 4.2. Now, next we'll look into the local maximum. As you can see in here, our local maximum is somewhere in between negative 1 and 1 as x-intercept. Now, as I mentioned, the graph is going to need a little bit of time, or you can call it space, to make this S shape. And that means that it is the local maximum here is going to probably be obviously not in the middle. In the middle we have the y-intercept, that's for sure, but it's going to be slightly further to the left. So let's check and see where exactly is going to be. And I'm going to start off with negative 0. Let's say 2 in here. And we're going to have for the local max. So we're not looking at the middle between the x-intercepts. We're moving further to the left. So at x equals negative 0.2, we'll have the function at negative 0.2 equal to negative 0.2 plus 1, 1 minus negative 0.2 to the power of 3, and then negative 0.2 plus 2. So that will give 0.8 positive. This is 1.2 to the power of 3, and next we have 1.8. So let's multiply 0.8 by 1.2 to the power of 3, and then by 1.8, and we get 2.48 in this case. As you can see, we are going in the right direction here because we have the y-intercept at 2, and at negative 0.2 we're going a little higher, so we expect the maximum to actually be on the left side of the y-axis. So we're going to check with negative 0.3. Let's see what happens there. And at negative 0.3 plus 1, again 1 minus negative 0.3 will make 1 plus 0.3 power 3, negative 0.3 plus 2. So at negative 0.3, if you look at the values in here, that's 0.7 multiplied by 1.3 to the power of 3, and then multiplied by 1.7 will give 2.6. It seems that at 0.3, we are getting even a higher value, so that means that we need to keep going until we see that the y values now are going down. So at negative 0.4, we have negative 1 minus negative 0.4, so that's 1 plus 0.4 power 3, and negative 0.4 plus 2. And here we go again, we have 0.4 plus 1, 0.6, multiplying 1.4 to the power of 3, and then multiplying 1.6, and we get 2.63. Okay, so we are getting an even higher value in here, so we can check negative 0.5. I think that this is where we practically will have to stop somehow. So I just want to double check here. So we have 1.4 power 3 and negative 0.4, 1.6. Cool. Now, at negative 0.5, let's see if the numbers will be going down now. 1 plus 0.5 power 3, and then negative 0.5 plus 2. So we got 0.5 here, 1.5 power 3 here, and 1.5 here. So 0.5 times 1.5 to the power of 3 times 1.5 would be 2.53. So numbers are going down, which qualifies this point, this point with coordinates negative 0.4 for x and 2.63 for y as our local maximum. So we'll record this as well. And we have 0.4, comma 2.6. One decimal is more than enough. How accurately can we plot them on the grid anyways, right? So So now that we have the local min and max, we have almost everything to shape our graph. So let's get to work. So we're going to keep our intercepts there. Very important. Negative 1.6, negative 4.2. So negative 1.6 will be somewhere in here. Negative 4.2 is the respective value. So it's going to be somewhere in here, the local minimum. And for the local maximum, we said that it is at negative 0.4 and 2.63, so a little bit more than halfway. So somewhere in here. And there goes our graph. So now we're going to try to draw a nice smooth graph here. So here we go. We're going to come from the second quadrant, hit the x-intercept. At the minimum, we're going to make a turn to go back up to x-intercept of negative 1. Going to hit our maximum here, come back to the y-intercept, and prepare to make an S shape at the next intercept, or a third order root, and there goes our graph. Beautiful as ever. Now that we have our graph, we can determine the intervals of increase and decrease. So notice how the function is decreasing and then decreasing in here. So we're going to say that the function is decreasing for what values of x? Well, this is an arrow from negative infinity then to negative 1.6. I think it is kind of nice to write the coordinates, not a must, but negative 4.2 here, and this is negative 0.4 and 2.63 or 2.6. That's the local max, and this is the local min. And the function will start decreasing from negative infinity to negative 1.6, and it will decrease also in the interval from negative 0.4 all the way to infinity, because notice that the function is decreasing all the way here. Now the function is increasing only in this little section in here between the min and the max. So we'll say that the interval of increase is between negative 1.6 and negative 0.4. Now we have to determine the intervals where y is positive or 0. So remember that positive or 0 means that the graph is above the x-axis, and we'll include the zeros as well. So it seems that the graph is above the x-axis from negative infinity to negative 2. So remember, intervals where the function is positive or negative need the intercepts, right? So the x-intercepts are our guiding points, whereas intervals of increase and decrease, we need the local min and the local max points, right, as our key values. Now, from negative infinity to negative 2, the function is above the x-axis or 0 at negative 2. And then we have the function above the x-axis from negative 1 to positive 1, including the zeros. It is less than 0 between negative 2 and negative 1, and from 1 to infinity. And drawing the intervals, obviously. What do we have left? The end behavior is the easiest. And we are going to say that on the right hand, when x approaches infinity, the y values are going down to negative infinity. And on the left end, the y values are heading up to positive infinity. And this was the recording for this particular example. I hope you found the instructions useful. Thank you for learning with me. Bye for now.